All right, class, let's finish this section and solve just a few more problems as you saw on your notes. So, I'm asking you to find the instantaneous rate of change in this function, specifically when x is equal to 9. So, what does it mean to find an instantaneous rate of change in a function? Well, to find an instantaneous rate of change in a function simply means to find its derivative, yes? Okay, so it's really the problems we did on the previous page, just wrapped in a little bit of a different story. Now, what you could do is make x be 9 from the beginning, but really much easier and a much better practice would be to first find the derivative and then plug in that 9. Okay, so how do I find the derivative of this function? Okay, again, better practice. And by the way, I keep picking different types of functions so you could see different tricks of dealing with it. So we had a linear function on the previous page, a quadratic function, a rational function, the 1 over x squared, and now we're going to go over a radical function. So what does it mean to find this derivative? Okay, so here it is. It's the limit as h approaches 0. So what I'm going to do is plug in these values. So f of x plus h is going to be the square root of x plus h plus 4 minus f of x is the square root of x plus 4 all over h. Now, sure enough, one thing I can do is those 4's are going to go away, right? So the plus 4 from here and the minus 4 from here, these are gone. Okay. All right. So this is what I am left with. The limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Okay. How am I going to make these h's go away? Don't just cross them out, okay? It's just, that's not mathematics, okay? Yes. Oh, we need to make h's go away. Well, I'm just going to pretend they're not there. That's not how we're dealing with it, okay? I have to still do this properly. So the problem is, how do I make these get out of the radical? And by the way, you can just subtract under one radical symbol. That's not a property of radicals. You can multiply into one radical, you can divide out of one radical, but not add or subtract. Okay, so in other words, what? The square root of 5 minus the square root of 3 does not equal to the square root of 2. Okay, so what do we do? Well, again, another trick we've learned in algebra. That would be called rationalizing. So when you wanted to make radicals go away out of the denominator, now we want to make them go away out of the numerator, but that's the same idea. You multiply top and bottom by the same two radicals, but you switch the sign in the middle. So that was called rationalizing. And that's anytime you have radicals in the denominator, you want to get rid of them. Now we want to get rid of the radicals in the numerator, so fine, we're rationalizing the numerator. So how is this going to be helpful? Okay, be a lot. So I'm going to distribute these. So what's the square root of x plus h times another square root of x plus h? I'm distributing, yes? So whenever you multiply a square root to itself, the square root actually goes away. So that's an x plus h. Plus the square root of x plus h times the square root of x. Those are different ones. So as I said, you're allowed to multiply under one radical symbol. Okay. Now continue here. Negative square root of x times the square root of x plus h is just that. Okay. And finally, negative square root of x times the square root of x, that's just an x. The bottom, don't need to distribute it, so keep it as it is. Why am I not distributing this? Because remember, we want the h to be a common factor so we can reduce it at the very end. So look at this. Does anything go away? These two happen to be one and the same thing, a plus and a minus. This is really why we switch the signs. Because anytime you multiply, here, let me take this, any plus minus same exact two terms, what's going to happen to the middle two terms? The middle two terms are going to cancel out, right? You get an x squared plus xh minus x, xy plus xy and then minus y squared. So the o and I in these products always reduce, yes? So that's really why we're switching the sign. So you could just left with the x squared minus the y squared, and that makes them perfect squares. All right. All right, is there anything else that goes away? Yeah, the x, nice. Thank you very much. What's left? Ooh, the only thing that's left in the numerator now is just this h, which I anyways wanted it to be a common factor. So look at that. I'm just left with h at the top, which now is going to take this h at the bottom, because now it's a common factor. Boom. So that's gone. Great. So can I now plug in 0 for h just to save some time? So now I'm finally ready to evaluate this limit. So again, these, when they reduce, I'm left with a 1, yes, in the numerator. H goes into h 1 times. Same thing here, but 1 times anything is just itself. So when I plug in 0 for h, what do I get? The square root of x plus another square root of x, which, by the way, equals to 2 of them. Okay? So this is the derivative of this function at any random x value. What do I want it? I wanted the derivative specifically when x is 9. So great. All I have to do is now plug in and find that derivative at 9. Okay, so make x 9, yes. Square root of 9 is 3 times 2 is 6. That's your answer. Done. Okay. All right. So we're going to do the same thing, but I'm asking you a different story, and different story is that I'm asking you to find the slope of the tangent line to this function when x is equal to 6. Great. What does it mean to find the slope of the tangent line? It means to find the derivative, right? Where? At 6. Okay. So let's find the derivative first. That's the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's the limit as x approaches 0 of, what is f of x plus h? Is 4. Plug in x plus h for x, minus, again, f of x, which is 4x plus 7. Okay, so that's the limit as h approaches 0 of, just the desk. Okay, so distribute in the 4. So 4x plus 4h plus 7 minus 4x and minus 7. Again, be careful distributing in the minus sign. So, do any of these terms go away? Yes, the 4x goes away. The 7 goes away. What should happen is only h terms should be left behind. So, can we save some time? I have a 4h divided by h. That's just the 4. And plugging in 0 for h would just leave me with a 4. as we saw on the example on the previous page, this is a line, right? It's a linear function. The slope of this line is 4, right? The line goes up at the same exact rate of 4 at any point x, right? Any other tangent line would just be a 4. So if I plug in, if the derivative of x at any x is 4, what's the derivative at 6? Well, it's still a 4 because it's a constant function. It doesn't change values one bit, right? So the slopes are always going to be 4 because, again, it's a linear function. All right, but we practice a little bit more of algebra. Great. Finally, last problem here says the population of a certain town is given by this function. Many thousand people, where x is the number of years after 2000. Find f prime of 2 and interpret the answer. What does that mean? So, a population of a certain town is given by this function, this many thousand people, where x is the number of years after 2000. Find f prime of 2 and interpret the answer. Now, first of all, let's see this. What does f prime of 2 mean? It means to find the derivative and then plug in a 2 in that. Okay, that's the first part. Okay, so let's just look at this function really a little bit. X is years after 2000. So could you tell me what's the population of this town in 2000? So I'm just going to write on the back page here really quick. So just on a side note. Okay, 1,000 people. Great. Where x is years since 2000. So what happens in the year 2000? Well, in the year 2000, what's the value of x that I get to plug in? Well, that'll be 0, right? Because in 2000, it's 0 years since 2000. So if I plug in 0 in there, I'm going to get 100. That means what? By year 2000, the population of this town is 100,000 people. So this population started at 100,000 people. Okay, what would be the population, let's say, by year 2002? Well, in 2002, x is 2. So what's the population 2 years later? Okay, that's 412. 12 minus 10 is 2. By the way, if you would have looked at 2001, the population would have gone down to 98,000 people. But then it's increasing again, and we're getting to 102,000 people, right? Now, what we want to do is, this is a quadratic function. Yes, actually, it went still from 2000 to 2001. As I said, it had gone down a little bit, and then it's actually back up, going up. So what we want to know is, by 2002, what's the derivative of this function? In other words, what? Where is this function heading towards in 2002? So what do we expect is going to happen? Is this population on the way up in 2002, right? Is it increasing, and how fast is it increasing? That's what the derivative will tell us, okay? All right, not what happens at 2. Now, don't plug in a 2. Yes, where is it? It's the derivative at 2. So our first task, again, would be to figure out the derivative function. So I'm just going to find the derivative, which is, one more time, the limit as x approaches 0 of f of x plus h minus f of x all over h. Oops, not x, but h. Okay. So here's my function. What I'm going to do is I'm going to first plug in an x plus h. Minus, plug in the x all over h. Okay, so that's the algebra part. Now find the limit as h approaches 0 of, start distributing. So that's a 3 times x squared plus a 3 times 2xh, that makes it a 6xh, plus a 3 times h squared minus, whoops, no square here, just x plus h, 5x minus 5h plus 100, and then minus all the rest. So minus 3x squared, minus minus is a plus 5x, and minus 100. Great. Okay, so, oops, all over h, of course, but I was eager to start crossing things out. What's going to go away? The 3x squared, the 5x, and the 100. So all these terms always are going to have to be reducible from fx. So let's take a quick look. Are the terms left over all going to have an h in them? Yes, they are. Perfect. That's what has to happen. I have to be able to factor out that h. So of these terms left, let's factor out the h. What's left? 6x. 3h squared, take out 1h. You're left with 3h. And then minus 5. So sure enough, now I can reduce the h's. And now I can very well plug in 0 for h, because there's no more h in the denominator. So plugging 0 in for h will get us 6x minus 5. Great. That's the derivative for any random x. What do I want? I want the derivative specifically at 2. So when I plug in a 2 in here, 6 times 2 minus 5, that's going to be a 7. Yes? Okay. So the derivative when x is 2 is 7. What does that mean? Well, first of all, when x is 2, we are in year 2002. So let's write that down. So by 2002, or in 2002, what's going to happen? The derivative is the instantaneous rate of change, yes, in this function. What does this function measure? It measures thousands of people, right? So by 2002, the population of this city will be changing, right? How does it change? Well, it's a positive, right? So we'll be increasing by how much? Again, remember, an instantaneous rate of change, right? It's a slope of the tangent line. It's a rate of change. It tells me how the y's change with respect to the x's. So any derivative is a rate of change. So its units will be y values per x value. So we'll be increasing by what? 7,000 people. Yes? So we can write 7,000, where you can write the words 1,000 people per year. So after 2002, the population of this town should be increasing at about a rate of 2,000 people per year, right? That's the slope. 7 means 7 over 1, right? So 7 over 1, 7,000 people over 1 year. So in other words, what? Whatever we have found in 2002, it was 102,000 people. So what we're doing is we're expecting this population to increase by another 7,000 per year. So by 2003, we're expecting the population to be about 109,000 people. Now, that doesn't mean it's exactly, it's just an approximation. It's telling you where it's heading. So we might as well look at what happens by 2000, a year later, right? By 2003. So it's 3 times 3 squared minus 5 times 3 plus 100. Again, that's just an approximation, right? What is really happening from one to the next is not necessarily what happens at the point itself, right? We've looked at secant lines versus, where was it? Here it is, all the way back in the beginning. So we looked at secant lines, right? What happens one more away versus really what happens at the point itself. So it could be a difference, but it's an approximation, right? So right? That's where it's heading at that moment in time. So let's see, I'm not promising much. That's a 27 minus 15 plus 100. That's 12, so about 112,000 people. So we expected 109, yes, but again, that's just because a year later, in fact, it's really just pretty far from what happens at the moment, right? So again, this tangent line versus what happens a year later could be slightly different, okay? All right, so this is what a derivative is. It's telling you where a graph is heading instantaneously, right? At that specific exact point in time. Yes, things might start going even faster or slower, might temper down. But at that point in time, in 2002, the population was increasing at a rate of 7,000 people per year, which is this many people per day, right? Or this many people per month. So we don't want to maybe look at the whole year, but this is where it was heading at that point in time. Okay. Now, derivatives will be a huge application. The one part that's extremely annoying is all this algebra that we have to go through every single time. So what would be really helpful is if we could find a way to find the derivative without doing all this algebra. So can I go from here maybe quite right away here, you know? So that's exactly what we'll be exploring in the next sections, rules for derivatives. So yes, you might not like formulas, but I bet you in this case you will welcome them quite a lot, because you will just be looking at this function right here, and in 2 seconds times you'll be able to tell me the derivative is 6x minus 5, just like that. I don't even know what the answer is, but I'm looking straight at this, and I know in 2 seconds that the derivative is 6x minus 5, which, yeah, that's what it was, without all this computation. So formulas are coming up next.